Hey, welcome to our lesson 15 for week 5. This lesson, I know it's like what place value powers of 10, isn't that babyish? Well, we're trying to take something that is implicit or intrinsic in you, something that you just know and you've known for a long time, and we kind of take it for granted then. We're going to try to make it extrinsic. We're going to look at it and analyze it and see how it can be applied in more difficult kind of situations. So, bear with me. I like going through this because it's something that kind of shows you, I don't know, the beauty almost of math, all right? I mean, it's pretty impressive how they came up with this system when you think about it. And first I'm going to talk about numbers. Numbers are, remember, just adjectives, okay? They tell us or describe something, all right? They tell us, a count of something or a measure of something, okay? And that thing is what the decimal point represents. That's the unit, okay? So when we start talking about counting or measuring that thing, this is what it is, whether it be like, apples or money or length or weight, okay? And we start with ones, right? And anything to the 0 power, remember, lift this up a little bit, is 1, okay? And then tens. Now, our whole number system is based on 10 because we've got 10 fingers that we could use to count. So we have 10 digits, 0 through 9. As soon as we get groups of 10, we start representing numbers by using different columns or place values, right? And just keep repeating these 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But where we place them in these columns gives us more quantity, right? So a group of 10 ones, a group of 10 tens, right? So everything's based on this 10 times more than the previous one, right? And 10 times more, that increases that exponent, right? And then 10 of these, 1,000, 10 thousands, 100 thousands. And then you'll notice that we start to change names. 1 million, 10 million, 100 million, 1 billion. And you see this other pattern kind of evolving, right, where we group them in groups of like 3, okay? So we call these groups families or periods. If you recall, I had this poster in our classroom. We would name these, and they were kind of color-coded like this. So I'm going to try to do that real quick for you. That these families or periods have this repetition of 1, 10, 100, 1, 10, 100, 1, 10, 100. And we have this name of the family, okay? So this is the ones family. Okay, and I'll bet you can guess this is the thousands family. And this is the millions family. And so every time we get a group of 3, we separate them, remember, by these commas, okay? So every comma has its own name also. Just like this decimal point has a unit measure, meters, let's say. Here's where we get this comma. That comma is 1,000 of that unit. Here's a million of that unit. A billion, trillion, quadrillion, right? We could keep going. We just have these families of 3 with different names for that family, repeating 1, 10, and 100, right? Now, since they're all 10 times bigger, you'll notice that we're marking these with an exponent of, however many groups of 10, and 10 is our base 10 system. Now, as we get smaller, remember, these negative numbers represent small numbers like decimals or fractions. So it's like dividing by that amount of 10, right? So tens, hundreds, thousands. And you start to see some repetition in here, with the names thousands, millions, billionths, right? But we don't call that part families, okay? Okay, so hopefully this was just, yeah, got it, know it, right? But it is really important that we have a thorough understanding of it to understand the rest of this, right? So when we are asked about, well, what does that 6 mean? It doesn't mean 6, right? It means 6 because of where it is in the thousands place. 6 times that place value, 10 to the 4th, 60,000. So the 6 is in the 10,000s place. And so we could represent it like both of these, right? What about the 7 up here? Well, 7 up, huh? The 7 is in the 10ths place because it's 1 to the left of the unit. So it's 1/10 of it. 7 times 10 to the -1, or 7 times 1/10, or 7/10, or 0.7. All of those represent the same thing, right? Okay, so hopefully you've done really well up into this point. This might be a little new, but it's going to be kind of important that we understand that these digits, based on where they are placed, okay, that is really just a 3 in the 10,000s place. This is really just a 7 in the hundreds place, right? So it's that digit times its place value tells me its quantity, right? I want to keep in mind down here, 2 times 10, oh, that would make it seem like it was a big number, but remember 10 to the 0 is 1, okay? Now the other thing I want to talk about is that sometimes you get teachers who say, oh, that's just how many zeros there are. You know, well, sometimes that's true and sometimes it's not. I don't want you to think about that. I want you to think about its place value. From this decimal place, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 place values that decimal point would have to move, right? Now, just lost my train of thought on that, darn it. Oh, well, hopefully it'll come back to me. Couldn't have been that important, right? Okay, we're going to flip this over, and hopefully you saw the pattern here on these charts. We're just multiplying by 10, right? And recognizing, okay, well, if I take this very small number and make it 10 times bigger, all that happens is I moved that decimal place over a column, a place value, because we have a base 10 number system, columns of 10, right? If I make this 10 times bigger, again, I'm going to move the decimal point in a way that makes that number grow, right? And the number's going to grow as this number 4 starts to move more and more to the left, away from the decimal point, okay, in this direction, closer to it when we're going this direction, okay? So we see this, you know, see the pattern that we're seeing with the zeros, right? We're dropping zeros from the left of it. These are just kind of place value holders, right? I could add zeros to this as long as I put the decimal point on it, right? Adding zeros to this would not change it. Adding zeros in front of this would not change it, or after it, right? Same thing over here. This is where it probably makes more sense that, hey, it's not about adding zeros, right? It's about moving the decimal point, right? So if we are taking a 10th, it's like dividing by 10. It's getting 10 times smaller. So I'm going to make this number smaller by moving it to the left. Same thing here, smaller by moving it to the left. So we see this pattern where the decimal point, right, was here, and it's moving over and over, and we're getting less numbers on the other side or the left of the decimal point. We're getting more numbers in the decimal place values, okay? So it's getting smaller. All right, so what are we kind of summing up here? That in a multi-digit number, a digit in one place represents 10 times as much as it represents in the place to its right, and 1/10 of what it represents in the place to its left. So that's just that relative thinking, that, you know, relative to what's in front of it, to the left, but what's next to it on the right, what are their respective, you know, relationships, okay? All right, so if we take that idea and apply it here with some money, sometimes that's the easiest way to think of decimal values. If we have 1, that's a unit. 1 what? 1 package. It costs $2.46. Well, 10 packages would cost 10 times that. Anytime we're going to multiply by 10, we're going to make it 10 times bigger, meaning more digits will be to the left of the decimal point. 100 times bigger. One more column that we move it over, one more place value of 10,000. Notice that we've moved it 1, 2, 3 times, right, to make it bigger. 1, 2, 3 times to make it bigger. Now, 1/10, we're going to make it smaller. And to make this number smaller, I have to move my decimal place this direction. So now it's 0.25. Notice that I rounded that because we couldn't say 0.246. I'm not going to charge you, 6 thousandths, right? Or a fraction of pennies, right? Okay. A couple kind of fun, I guess, we kind of wish it was closer to Easter when we ask these kind of questions about peeps and jelly beans, right? All right, so we get 1A peep, right? 6.2 grams. How much do you expect 10 peeps then? Well, 10 times bigger moves that decimal point one place to the right. So 62 grams. A lot of this is just common sense. I know that you know it. You could do it without thinking. Like I said, that's intrinsic in you. But really make extrinsic what you know. You know that. Pay attention to what it is you're doing. So he puts 10 jelly beans. The scale is 12 grams. So one jelly bean is going to be 10 times smaller. We're finding 1/10 of it. Dividing by 10 means we're going to move it back to make it smaller. One space left. Again, just think about it. Make it more obvious in your mind what you're doing. So it's thinking about your thinking. That's called metacognition, all right? All right, and then this one, 10 cinnamon bunnies, 88.2 grams, 1,000 of them. Well, that is 100 times more, right? We moved that decimal twice, so we're going to have to move it twice here. Wait a minute. Oh, that's 10 of them. 1, 2. Did I do that one right? Yeah, that's right. 2 place values. 1, 2. Now, this one I don't really want to spend too much time on, because it's not quite under our concept, but it is kind of good to know that if we know that the bunny is 8.82, one bunny, not 10, but 1, and one jelly bean from up here is 1.2, right? Well, just how many 1.2s are in 8.82? And that's where I got that answer. Okay, all of this is going to be really important for us next week. So hopefully you did really well on this. If not, I would spend a little time going back and maybe adding to your worksheet, okay?